Okay. Hi everyone, I hope you're all doing well amidst this COVID situation. We're all still here to learn though, so today we'd like to teach you about an interesting classification technique. My name is Sergey, and with my teammates Matthew, Rashid, and Urko, today we're going to be taking you through our presentation on extra tree classifier. So in classification world, really, we've been following this lineage of starting with decision trees. We could only get so far with decision trees, so we upgraded to random forests. And let's look back and remember the basic intuitive premise of random forests. It's to make multiple decision trees that all make different mistakes in classifying data. And in order for these decision trees to make these different mistakes, we add in some randomness. And the randomness is achieved through bootstrapping and also randomly choosing subsets of attributes to build each node at each individual tree. Each of these trees alone are poor classifiers, but when you put them all together, right, or ensemble them, they make for a powerful classifier. And that's why random forests and extra trees, as we'll see as well, are part of the ensemble learning methods. So extra tree classifier is kind of like a variant of random forest. It follows a lot of the same fundamentals as random forest. Like random forest, it builds multiple trees and averages them. It also uses random subset of features to consider when splitting a node at each tree. But there's two big differences between extra tree classifier and random forest. The first one being that in random forest, the way that splits occur, they're calculated, they're optimal, and they're based on the underlying purity of the split, right? In extra tree classifier, the splits are completely random. And the second big difference is that the whole sample is used to construct each individual tree. So there's no bootstrapping, whereas in random forest we had bootstrapping. And this is why extra tree classifier, it's also considered or has the name extremely randomized trees. So I mean, it has its advantages and its drawbacks. One of the main advantages to extra tree classifiers that it has over any other classification model is that it has a lower variance. I mean, for each individual tree, the variance is higher, right? Because there's a possibility that the possibility that an irrelevant attribute is used to split a node is as high as the possibility of a relevant one, right? The probability of it being chosen is the same. Although it causes high variance among individual trees, when you average them out, that's compensated for. It also has a faster runtime because of the randomness of the splits. Obviously, I mean, calculating what the optimal split would be takes more time than just randomly choosing a split. And because of this, it handles data sets with large number of attributes better and faster, right? Looking at the drawbacks now, there is a possible increase in bias because if you do split on an irrelevant attribute, it's basically the same thing as randomly splitting the sample, right? And you're decreasing the sample size, which increases bias. And this bias is not compensated for by averaging all the individual trees. Also, it is a black box algorithm and arguably less interpretable than random forest or other classification techniques because of the randomness of the splits. We'd have a hard time explaining why the algorithm split, right? So where can extra tree classifier be useful? It's particularly useful because of the lower variance in situations where the data has a lot of noise. It's also useful in any situation because of its fast runtime where efficiency is needed, is valued, and just overall where random forest is useful, extra tree classifier is most likely going to be useful as well. They are very, very similar. Here's an example of a problem where extra tree classifier was useful in predicting protein disorders, and it's a data set that is particularly noisy, and so it was useful there. So now I'm going to pass it on to my colleague for the rest of the presentation.
All right. All right. So now we're going to talk about the differences with other methods. So we're actually with one specific method, which is actually random forest. We're going to compare random forest to extra tree classifier. Well, we basically picked random forest because it is actually the one that is the one method which is actually most similar to extra tree classifier in our point of view. So, in our opinion, so in order for us to see why extra tree classifier is actually is more useful and is actually more effective, well, we should compare it to one specific method which is actually similar to it actually. So we're going to compare it on three levels. First of all, we're going to talk about problems with large number of numerical features, and then we're going to talk about the statistical point of view and the functional point of view. So regarding the first point, with the issue with a large number of numerical features, well, this idea actually is rather productive in the context of many problems characterized by a large number of numerical features varying more or less continuously. And you may ask, why is that? Well, actually, this leads to often increased accuracy thanks to its smoothing, and at the same time significantly reduces computational burdens linked to the determination of optimal cut points in standard trees and in random forest. This means that, well, basically, even though, of course, most of the time accuracy of the two methods are actually pretty similar, if at some point there has to be some difference in terms of accuracy of both in between both methods, extra tree classifier tends to be extra tree classifier's accuracy tends to be slightly above random forest's one because of this reason. Then, from a statistical point of view, well, actually, extra tree classifier drops the bootstrapping idea, which leads to an advantage in terms of bias. Whereas the cut point randomization has often an excellent variance reduction effect. This method actually has yielded state of the art results in several high dimensional complex problems. That is regarding the statistical point of view. Then we're going to move on to the functional point of view. So this extra tree method produces piecewise multilinear approximations rather than the piecewise constant ones of random forests. So what this actually implies is that in a way a tree classifier is able to adapt approximations in a more efficient way and actually more, let's use the word accurate way, because like I just said, random forest it uses actually constant approximations, which is actually less useful to us in general. Now, moving on to real world applicability. So, here we picked actually two examples. The first one being facial recognition, because actually this example shows the use of forests, of trees, to evaluate the importance of the pixels in an image classification task. So as you can see, for instance, in this image right here, we could see that the harder the pixel, the more important it is. So this is actually an example in which extra tree classifier is used. So here, well, this actually applies to several examples, such as, for instance, smartphones or iPhones. These phones actually use systems, facial recognition systems, which use extra tree classifier to unlock the phone and unlock the screen. Also, this is used, for instance, in terms of security, in security issues. For instance, in order to look for one specific person who has been recorded by a camera, while his face or her face will be run through an entire system, which uses extra tree classifiers in order to recognize the person.
All right, thank you very much. So today for my part, I'll be talking about an example that I developed that shows a little bit of the differences between extra trees classifier versus random forest. And at the same time, we'll show you a little example of how to develop an extra trees classifier model. So for this example, we use the churn dataset, the dataset used in class, where our y variable was the churn rate, 1 or 0, depending on whether or not the customer stayed or decided to leave the company and take his services with him. And our x predictors, we have 8 variables. We have whether or not the customer had an international plan, had a voicemail plan, the number of voicemail messages stored, the number of daytime minutes he had included in his plan, the number of evening minutes, nighttime minutes, international minutes, and even the number of customer service calls that he made to the company while he was with them. So as you can see, for this, we used from sklearn the package extra trees classifier. And as you can see in the next slide, the purpose was then to calculate the confusion matrix, accuracy, precision, recall, and the F1/AUC score. And to do that, what you see on the screen is the model for the extra trees classifier. But I also wrote the exact same code for random forest using the exact same, random state 0 and 100 trees, because as we know, the more trees we add, the more it requires computational power. So for the purpose of this presentation, we decided to stay with 100 trees for both models. And because this presentation is about extra trees, on the screen, I will only be showing the extra trees model code, but then we will also be comparing with the results from a random forest. So once we calculated these metrics, we wanted to compare them. And we found that basically random forest at first glance seems to be better overall than extra trees. It has a higher accuracy, a higher precision, higher recall, higher F1 score, higher area under the curve. Even though extra trees only have a slightly higher true negatives and false negatives, random forest has slightly higher true positives and false positives. So before making any assumptions, we decided to verify these results by doing some hypertuning. As you can see, we performed the hypertuning for both random forest and extra trees classifier. Just to give you a quick example, we found that the max feature that returned the optimal value for extra trees classifier was 8 features, which is the same number as the variables that we have. But for random forest, we found that it was 5. So we found different hyperparameters for each model. For max depth, we found 18. Min sample split, we found 4. Min samples leaf, we found 1. And for bootstrap, it was 0. Then we wanted to test again the confusion matrix, precision, recall, F1, AUC, again using the new parameters. And we did that for both models, extra trees and random forest. And we found, to our surprise, that after post-hypertuning, now extra trees suddenly had a higher accuracy, a higher precision, higher recall, higher F1 score, higher area under the curve. It is also interesting to note that the accuracy score for random forest did not change following the hypertuning because basically the new parameters were not affecting the accuracy. So we wanted to go a little deeper in our comparison. And even though this is not data mining per se, it is interesting to see that the R squared score, even when plotted, is slightly different than the random forest for extra trees. And we also decided to calculate the feature importance for each model, for each variable. And we were able to create a bar chart. And we saved the images that I'm going to show you in a second. So first, we found that extra trees had a higher, slightly higher R squared score, But this is a stochastic result, meaning that every time we ran it, we were getting different R squared, slightly different, but every time it was just slightly higher for extra trees. What's also interesting is basically you can see that it's a little steeper. This plot that you see is the increase in R squared when going from 0 to 9 trees. I did test it with 100 trees, but you don't see the changes as well as when only using 9 trees. And you can see that with extra trees, it's just from one tree to the other, it's quite steep. Even though it's very similar than random forest, it's just that for extra trees, we see a little bit more drastic changes in R squared as we increase trees. And last but not least, the feature importance that we found here for extra trees versus random classifier. As you can see instantly, it's easier to analyze which variables are more important for extra trees than it is for a random forest. For example, we see that the number of daytime minutes are clearly, and the number of customer service calls are clearly the two most important variables for extra trees. Whereas for random forest, yes, daytime minutes is clearly more important, the most important, but you can also see that even evening minutes is second place, but very, very, very closely followed by customer service calls, which is third place, which makes it harder to decide which variables are actually more important because the changes are so small. And what this created was the realization that with extra trees, it is much easier to decipher the variables importance. For example, after customer service calls, yes, it may be hard to see which one is more important between voicemail plan and evening minutes, but you can see that they're both a lot more important than their other variables. So, of course, it really, again, it doesn't mean that extra trees classifier are definitely better than random forest, but using this example, and you can see that it is more accurate and that it is better to decide which variables are more important. So thank you very much, and I will let my colleague speak now.
All right, so next we're going to dig a little bit deeper into extra tree classifiers and trying to compare them with some other models that exist, and going back to random forest to understand how extra tree classifiers is a really powerful tool. So what we're going to look at here is something called the iris flowers data set. It's a pretty old data set. It was made in 1936. It's used in a lot of pattern recognition literature, and in our context, it's used in a lot of machine learning algorithms to intuitively understand how they function. Now, in this data set, each observation, so in other words, every row in the data set is a type of iris flower. And so it includes information such as its species, but also some specific dimensions of the flower. And now in this data set, there are 3 species of flowers. So as we see the last bullet point there, we have all 3 species listed. And also they have 4 features. So if we look on our X variables, we see here that there's 4 types of features. So looking at the lengths and the widths of different parts of the flower. And in total, there's about 150 instances, so 150 observations. And so each of the 3 types of flowers has around 50 observations. And our Y variable that we're predicting here is the actual class of iris plant. So basically, as those Y variables include the iris setosa, iris virginica, and iris versicolor. So those are the 3 Y variable outputs that we have. What we're going to do next is to actually move here into Python to kind of do a little demonstration and understand how extra tree classifiers works. So firstly, this block of code, we're going to actually load the iris dataset. Now, what's really useful about it is that it's actually already found within Python. So it's a built-in dataset, which is really great. It's easy to use. And so we have this uploaded right now. Now, the next thing that we're going to do is look at something called decision stumps. Now, a decision stump is basically a type of model that has a one-level decision tree. And so one level, you can think of it as having one internal node that's connected to the final root node. Now, what it does basically is that the decision stump, it makes its prediction based on the value of a single input feature. And what this means is that if we look at, for example, we're going to take 1,000 decision stumps and compare it with one single decision stump to see if these two models have some sort of difference in them. And when we split the data set, when we define the stump, and we try to make a prediction, we try to determine what's the accuracy of our model. Whoops, sorry. So let's run again. There we go. So over here we have the accuracy of the stump, which is 55%, but it also equals the accuracy of the ensemble of decision stumps, which is 55%. Now, you might be wondering, well, why is it the case? If we have 1,000 stumps, shouldn't we be getting a more accurate result? But the thing is that when you're running 1,000 decision stumps, you're actually running the same model over and over again 1,000 times, which is why you're getting the same accuracy of 55%. And so we see it's not a very useful accuracy. So it's not something that clearly indicates it's a very powerful model that we can use with this data set. Now, the next thing that we're going to do is if we go down here, we're going to actually take a look at random forest. And in this case, we're also using decision stumps, but we're going to try to introduce some variation into our model here. And basically, the way we're going to do it is as follows. So basically, we're going to create a bootstrap. And the idea is that it's going to be created by randomly sampling the training data set with some replacement. And so we also know that the size of the actual bootstrap is going to be equal to the size of the training data set. And also, in order to form any of these root nodes, so the final node that's formed, the best split is going to actually be determined by searching in a subset of randomly selected features. And the way that we select these random features is basically by, I'm going to draw here. So the way we're going to select it is by using something that looks like this. The square root, there we go. So basically using the square root of n number of features is the way we're going to do it. And keeping in mind, in our data set, we have 4 features, which means that we're going to have every decision stump will basically inspect 2 out of the 4 total features that we have. And just for reference, those features are again here, these x variables, the sepal length, the sepal width, the petal length, and the petal width. And also we're going to keep in mind that the maximum depth of the decision stump is going to be equal to 1. Now, if we run this, let's see what we actually get. So I'm going to close out of the drawing here. And when we run this, well, look at that. So first we have an accuracy of the stump, which is 55%. So we've kept the same stump that we had before. Now we're producing a random forest with accuracy of 95%. I mean, that's pretty remarkable that we're getting this result. Now, what's really interesting about it is that we're using a lot of these decision stumps with low accuracies in order to generate this forest. And so by introducing some variation in our code, what this results in is basically a more accurate result. And so we know that we introduced this variation when we added these bootstraps, which were created by sampling some of the training data set with replacement and allowing the stumps to basically search only subsets of randomly selected features in order to split that final root node. Now, that really goes to show just how powerful random forest is. But now let's turn our attention to extra tree classifier down here. And if we do this, what we're going to try to understand is how extra tree classifiers really differs from random forests. Now, what we're going to do here is, so kind of similar to random forest, but we're going to try to introduce some additional variation. And this is how we're going to do it. So firstly, the available data that we're going to use is in the training set, which is going to actually be used to build each of the stumps. Also, what we're going to do is, in order to actually create the final root node, the best split is going to be determined by searching in a subset of randomly selected features. And again, it's going to be the size of the square root of n features. So that's why I've brought this down here with us for reference. And also, we're going to try to make sure that the split of every single feature is chosen at random. So again, introducing additional variation. And again, the maximum depth of the decision stump is going to be equal to 1. So keeping in mind here that both the features and the splits are going to be selected at random. And so this is why it's also referred to as extremely randomized trees. So it kind of builds off of the concept of random forest. And also, we understand that because these splits are chosen completely at random for every single feature in the extra trees classifier, we also understand that it is actually less computationally intensive to run this type of code compared to a random forest. And because of that, it's often the case that this kind of extra tree classifier is actually much faster and efficient compared to random forest. So let's see what we're going to get here when we run this code. And we'll look at that. So up here, we had previously with random forest, we had a 95% accuracy. And now, so again, referring to that 55% accuracy for the stump, we actually have the same accuracy of 95% with extra trees. So now I want to go back to our presentation. I'm just actually going to remove the annotation. There we go. So what do these results mean? Let's try to understand how this actually applies to extra tree classifiers, how we've compared the different types of models that exist. So kind of a summary, we had the decision stump and the ensemble of 1,000 decision stumps, which had 55% accuracy. And the ensemble just reran the same model over and over again. With random forest, we saw that there was some variation that was introduced, basically by building the decision stumps on bootstraps, and also because sampling the training set and allowing the stumps to only search for subsets of randomly selected features was used to split the root node. Now, when we compared this with extra tree classifier, again, we had 95% accuracy. But keep in mind, we introduced some additional variation when we use the extra tree classifier, because as we saw, since the splits are chosen at random for each feature in the extra tree classifier, we understand that there's less computational power that's needed to run this compared to a random forest, and so it's much faster. Now, to kind of summarize the whole presentation, just some key points that we want to mention. So firstly, understanding, well, why extra tree classifier? Why is it so useful? Why is it such an interesting algorithm? Well, firstly, as we mentioned, it's less computational power than a random forest. We also know that the results that are produced with extra tree classifier tend to have a very high accuracy. We also understand that there is less variance when you use a model like extra tree classifier. And also, as we saw from Rashid's example, where we showed the graphs of importance of features with random forest and with extra tree classifier, we clearly saw that visually it was much easier to see the importance of features when we used extra tree classifier compared with random forest. So thank you very much for listening to our presentation. We really appreciate it, and we hope you enjoy the rest of your day. Thank you.